The first definition we're going to look at is the term radian measure of the angle theta. It's defined as the ratio of its intercepted arc length, which is s, to the circle's radius, which is r. So in radians, it's basically defined, and as you get into word problems later on in trig, you'll see this s over r, which just means the arc length divided by the radius. Radians, you can think of it as another unit of measure for an angle, all right? Radians is actually going to be measurable as far as like if you were to take a tape measure and measure it out versus if you were just doing angular movement. And so when we think of angles, we typically think of them in degrees. Radians is another way to measure an angle. So if you were to look at this room, I could measure it in feet, or I could measure it in meters, or I could measure, and so there's different ways to measure. This is just a different unit of measure for angles. And so they define it this way: 2 pi r over r, meaning a full circle over with times the radius over the radius. So what it works out to is an entire circle in radians is 2 times pi, 2 pi, which is the same thing as 360 in degrees. A half a circle in radians is just 1 pi, which is the same thing as 180 degrees, so if you're talking about degrees. And so to convert from one to the other, you use that relationship. So 1 single pi is the same thing as 180 degrees. So if I were converting from degrees to radians, I would multiply by pi over 180. If I were converting the other way, let's say I was going from radians to degrees, I would multiply by 180 over pi. And so you can convert between those just like you convert between Fahrenheit and Celsius. There's a conversion multiplication piece that you can do. That's true from radians to degrees. And so now we're going to start moving into using radians. And this is when you really have to start being familiar with your calculator and making sure when you start calculating things, what is the problem set in, degrees or radians? And then what is my calculator set in, and make sure that they match, because you do have different ways to measure the same thing. You do have different ways to measure those angles. All right, so let's look at first just converting between the two. So you may be given something like this. Typically, you will see radians with a pi in it, but not always. So conversion's really easy. First of all, they will either have a pi in it. If there's a pi in it, you can typically assume this is in radians. You're not going to have a pi when you're talking about degrees. Or it will say something like radian, or at the top it'll say convert radian to degrees. All right, and so all we're doing is we're taking a radian measure and we're converting to a degree measure. So it would be like if I gave you Fahrenheit, instead I want it in Celsius. You would do a process to convert it to the other measure. And so that's what we're going to do. So anytime it is in radians and we're converting to degrees, we are going to multiply. So the process here is to multiply whatever you have by 180 degrees over the pi radians. Think about just conversion like you do in chemistry or in any other math class, right? So I start with pi over to radians. If I want to convert that, my radians now should be in my denominator. And so I'm going to say, well, that's going to be 180 degrees over pi. And that's where I'm going to get rid of those radians. You'll see those radians will cancel out and I'll be in degrees. Now, anytime I'm multiplying fractions, I'm going to try to cancel as much as I can cancel. So in this case, I'm going to cancel those pi's. I'm going to cancel that 2 with that 80 degrees. And you're going to see that pi over 2 converts to 90 degrees, which makes perfect sense, right? Because pi, as we said, is half of a circle. So if pi over 2 then would be a fourth of a circle, which would be 90, okay? Let's look at the next one. Negative 5 pi over 6. Negative 5 pi over 6. My final answer is going to be degrees negative. Remember, that is just movement. So I started here and negative movement would have gone clockwise, right? That's going to be true as well as far as degrees. So my answer should be negative when I get done with this one. I'm going to say negative 5 pi over 6 times 180 degrees over pi radians. I'm going to cancel those pi's. What else can cancel here?
The 6 and the
Yeah, my 6 and my 180. How many times does 6 go into 8?
30.
18, yeah, so 30. So now I just have 5 times 30 left over. Don't forget you have a negative. So this guy is going to be negative 150 degrees. All right. It does not matter that there is not a pi in it. We're still going to multiply it out. So if I have 1 radian, I am going to multiply that by 180 over pi. Now here's the thing, you're not going to leave pi and degrees in it. So you're going to actually take this and you're going to multiply it out, and you're going to say 180 divided by pi, and it'll typically tell you how to round. In this case, they rounded to 1 decimal place, so it looks like that. Again, the 3.5, while it doesn't look necessarily like radians, they did tell you that this was radians. So once again, you're going to actually multiply it out. You're going to multiply the 3.5 and the 180. You're going to divide by pi. And again, they rounded to 1 decimal place here. All right, that is converting from radians to degrees. If I have degrees, then I want to go to radians, I'm just going to do the opposite. So if I am converting from degrees to radians, I'm then going to multiply this by pi over 180 degrees. All right, so it's just the flip. So I'm going to take my 45 degrees and I'm going to multiply it by pi over 180 degrees. All right, these will reduce. So even if you don't see immediately how it reduces, you can start with like a 5 or something like that if you don't see what goes into all of it. So let's say you can't tell that it's going to reduce all the way down, which it will. You can divide by 5. So you can say, well, 45 divided by 5, and then 18 divided by 5, and then 30 divided by 5. Just reduce it. And then you can probably see this is going to reduce all the way out. Now you should be able to see 9 and 36 reduce all the way out, right? And so you can see that 45 degrees is pi over 4 radians. All right? It won't always be, something pretty. You may have a larger fraction. That's okay. But anytime you're going from degrees to radians, you're going to do the pi over 180. And again, if you don't see immediately that it cancels, you can, do your zeros there. You can say, well, what goes into 30 and into 18? Well, 6 should. And so then you're just going to multiply across once you reduce as much as you can. All right, questions on converting back and forth? All right, so arc length. So if I want to find the length of an arc, I am going to have my measure of my angle in radians, and then I'm going to multiply it by my radius itself. We did this another way in geometry. So in geometry, we used the circumference of a circle and multiplied it by the percentage of the circle that we had, all right? So for example, if I had this 60 degrees, let's just say that's what I have. That's 60 out of 360, right? And then I would multiply that by circumference. Circumference, remember, is 2 times pi times r. Okay, right? So far, so good. In this, I could actually reduce that to that, right? 2 and 360 reduce. So here I'm left with pi over 180 there times 60. That looks strangely like converting from degrees to radians, right? Times pi over 180. And then I have my r, which is 8. Because the circumference of a circle is 2 times pi times r. So remember in geometry, when we found the length of an arc, we would do the percentage of the circle that we had, the angle over 360 times 2 pi r. That's what we did in geometry.
I know, but like where?
All right. So in pre-cal, when you get into that, and in Algebra 2, when you're in the trig piece of it, it's telling you just take what you have in radians and multiply it by your radius. So if you have it in degrees, convert it pi over 180, and then just multiply by your radius. But it works out to the same formula as what we did in geometry. In geometry, though, we always had it in degrees. We didn't really use radians, okay? And so sometimes they'll give it to you in radians. Sometimes they'll give it to you in degrees. And then you're going to go from there. Now, I will say that they have a negative here. And we are talking about the length of an arc. Typically, it won't matter that it's negative. But when you start talking about direction, even though the length looks like it's negative, and typically we say a length cannot be negative, remember we're moving away from just a stagnant circle to like movement. So if you were to think for my people that are in physics, right, and you did vectors and all that good stuff, this is going to talk about, if you were talking about the movement of something, that negative is going to tell you a direction, not necessarily, hey, I'm taking a measuring tape out and doing this, okay? So if you're given a negative angle, keep in mind they're just telling you the movement of that angle is in the negative direction, just like if I were to say visually south. Well, from here, south feels negative, north feels positive, right? And so we get that because in our picture, we put it on a coordinate plane in our brain. And so that's all that's telling you. The length is negative. That just means the direction in which it moved from standard position was negative, all right? So let's look at these two examples. The first thing it tells you is that the angle measure has to be in radians, all right? And so if I want to find both of these measures, A and B, if I want to find A, I'm going to take the angle that makes up A. This one is already in radians. So if it's already in radians, then all I have to do to find the arc length is I have to take the angle measure that's already in radians, and I have to multiply it by my radius, which is 8. I can simplify it just like this. I'm going to get 6 pi centimeters, right? And if you measure that out, if multiply it out, they round to 2 decimal places here. All right, 2 decimal places. Let's look at the next one. The next one's the one that we just talked about. They have negative 60 degrees. That is not in radians, all right? So before I can use this formula, I have to convert it to radians. And then multiply it by my radius. And so again, these will cancel. I get negative 8 pi over 3. Obviously, length is not negative 8 pi over 3. That negative simply signifies which direction it moved, which direction that moved. The unit circle has a radius of 1 unit, and it is centered at the origin. The equation is x squared plus y squared equals 1. All right? So remember when we found radius, we would take the square root of x squared plus y squared. For the unit circle, hence the term unit, the radius is always 1. And so when we think back about what we did for bell work we used any point on the coordinate plane and finding those ratios. When we move that down to a unit circle, it actually doesn't change the ratios. Here's the reason. It does not matter if so let's base this off right angle trigonometry. So if I were to take this right triangle right here that they have, it does not matter if the right triangle is this big or if the right triangle is that big. The ratios between the sides will be the same. So what happens when you move it to a unit circle and say, okay, I want the radius of my circle to just be 1, all right? Because honestly, if the radius of my circle is 1, or if the radius of my circle is 300 miles, the ratios between the sides of those triangles for that angle measure will be the same. The ratio will be the same because ratios means equivalent fractions, all right? So if I were to take a radius of 5 or 6 with the same angle measure of alpha, it will have the same ratios for sine, cosine, tangent, and the other three as if I were to take it in a unit circle and say, well, my radius then is just 1. All right? And so what the unit circle does is it allows us to look at all potential ratios and say they all actually are going to simplify down to this. All right? If I were to reduce it down to the lowest possible, it would reduce to this. Okay? And so what we do with the unit circle is we create common angles, and we're going to create the entire unit circle based on common angles. All right? So let's talk about what this does then. If I look at what we did for bell work and I wanted sine of theta, I would say, well, that is y over r. Well, if r is 1, what does that mean my sine is? Y over 1. What is any number over 1? Just itself. So now on the unit circle, my sine is just my y value of where it terminates, okay, where that point ends. Cosine then. Cosine then was x over r, but once again, r is just 1 on my unit circle. So my cosine here is just x, right? And then the tangent doesn't change at all. The tangent is going to be y over x, all right? Y over x. And so when I start looking at the unit circle, instead of saying x and y, all right, I'm going to say, well, x value, that's just cosine of that angle. Y value, well, that is just sine of that angle. And so when you move it down to a unit circle, and my radius is just 1, I don't even have to consider the radius for sine and cosine and tangent. I can just consider my y value, my x value to do all three of those, all right? And so that's what we're going to build the unit circle off of. We're going to say, okay, we're not going to do any point on the coordinate plane. Any point on the coordinate plane can have a radius longer than 1, just like we did. On bell work, my radius was the square root of 17, all right? That's bigger than 1, by the way. All right, what we're doing with the unit circle is we're going to say, okay, we're going to take all the ratios down to just a unit of 1, a radius of 1. And that will account for the same angular measure, all right, all the way around. Now, here's what it is based off of, right? So let's look at these. If we look at these, if you'll recall from way back when, 45, 45, 90-degree triangle. My side lengths were exactly the same. And my hypotenuse was the square root of 2 times my side length. Well, let's take that to a unit circle, all right? Unit circle. These would be made up of my radius. Well, my radius on a unit circle is 1, all right? Which means this is the square root of 2 times 1. So if I wanted the sine of a 45-degree angle, that would be opposite over hypotenuse, 1 over the square root of 2. Well, if I were to rationalize that, square root of 2 times square root of 2, that's square root of 2 over 2. Same thing's true if I want my cosine. Adjacent over hypotenuse for 45 is going to be exactly the same thing. And opposite over adjacent is going to be 1. All right, so this is where we come up with those ratios for a 45-degree angle. This is true of all 45-degree angles, whether he is this big or whether it is a satellite dish millions of miles in space and it's a 45-degree angle at which it's set. The ratios will still be that way. Let's look at a 60. If you'll recall, a 60 degree was the shortest side. Your hypotenuse was 2 times the shortest side. And your longer side was the square root of 3 times the shortest side. Well, now this is representing my radius, okay? So now this is 1, which means my hypotenuse is 2, and my longer side is the square root of 3 times 1. And this is what creates my sine, cosine, and tangent for a 60, and sine, cosine, and tangent for a 30-degree angle. All right? Sine is opposite over hypotenuse. Well, the sine of a 30-degree angle, any 30-degree angle, is 1/2. Again, it doesn't matter if it's one I can draw on a piece of paper or one that I'm using to build a neighborhood and look across the street and look at those angles, all right? If it is a 30-degree angle, the opposite side compared to the hypotenuse of that triangle is going to be 1/2. Cosine is adjacent over hypotenuse. That's where we get the square root of 3 over 2. 30 degree is opposite over adjacent. Well, if I do 1 over the square root of 3 and rationalize it, it will be the square root of 3 over 3. You'll notice 60 just flips, right? 60 is opposite over hypotenuse. Well, sine of a 60 is square root of 3 over 2. Adjacent over hypotenuse, 1/2. Cosine of a 60 is 1/2. And then square root of 3 over 1, that's my tangent, all right? And so from there, we're going to build a unit circle. We're going to build a unit circle, all right? This is what you have in your hands. Okay? This is what you have right now. All right? So the first thing I want you to write on your unit circle are your degree measures. So we start with 0 degrees. 30 degrees, that's exactly 1/3 of a quadrant, all right? 45 degrees, that's exactly halfway into the quadrant. 60 degrees, that is going to be 2/3 of the way into my quadrant. And then of course we know that straight up is going to be 90 degrees. Hopefully we all know that one. I'm moving by 30 degrees again, 120. From 90 halfway through, the other side is 135. 60 away from that's going to be 150. And of course, a straight angle is 180 degrees. So you'll notice that every one of these is either a 30, a 45, or a 60, a special right triangle angle measure, right? That's where we get all of these from. So go ahead and put your degrees. So if I were to do 30 degrees and I were to do it in radians, all right? 30 degrees in radians, let's think about this. Half of a circle is 180, all right? So I have gone 1, 2, 3, 4, 5, 6. I've gone 1/6 of the way around a half a circle. A half a circle in radians is just pi, right? A half a circle is pi. 0 is just, well, that's easy in radians, that's 0. So 30 degrees is going to be 1/6 of the way around. So 30 degrees, if I were to convert it, would be pi over 6. Half a circle, and I've only gone 1/6 of the circle, all right? 60 degrees then would be 2/6 of the circle. What's another way to say 2/6? Well, that's just 1/3, right? 90 degrees would be 3/6 of the circle. What is 3/6? That's 1/2, right? 120 is going to be 4/6, also known as 2/3. So then 150 is going to be 5/6 of the circle. Here we're at 6/6 of the circle, right? Or the half circle, rather. 210 then is going to be 7/6 of a half circle. I've gone more than halfway, right? 240 then is going to be 8/6. We reduce it to 4/3. 270 is 9/6. That reduces to 3/2. 300, 10/6, also known as 5/3. 330 is 11/6. All right? So I'm going to point out a pattern because you are going to have to know the unit circle. All right? I just counted by 6, okay, to get those. You can certainly just convert it with radians. All right? But you'll notice that every 30-degree angle, all right? Let's not do that. So this is a 30-degree angle, right? Reference angle. We have a denominator of 6, right? This guy has a reference angle of 30 degrees, doesn't he? He also has a denominator of 6. 210 has a reference angle of 30 degrees. Look at his denominator, 6. And 330 has a reference angle of 30 degrees. Look at his denominator, 6, okay? 60, my reference angle for 60 is 60, pi over 3. 120 is my next 60-degree angle. That's 2 pi over 3. All right, 3 pi over 3, that's just my pi. My next 60-degree reference angle is 4 pi over 3. And my next 60-degree angle is 5 pi over 3. Does everybody see how this is building? All right? So your reference angles will always match, even in denominators. All right? Let's look at my 45. 45 compared to a half a circle is 1, 2, 3, 4. It's 1/4 of a half circle. Everybody agree with that? Yes? All right, so if I were to do this, pi over 4 makes perfect sense, right? Pi over 4 is my 45. All right? Then this is going to be 2 pi over 4, right? 90 degrees is pi over 2. Then what do you think 135 is going to be? 3 pi over 4. 4 pi over 4. 225 is my next 45-degree angle. That's 5 pi over 4. 270 is 6 pi over 4. 315 is 7 pi over 4. So you'll see that on the unit circle, if you can just walk around it, you're going to fill in all of your radian and degree measures. You're either moving by 30 degrees all the way around or 45 all the way around. All right? Questions on the degree measure? Now from this chart, if you will recall, my sine is my y value, because now we're talking about unit circle. My cosine is my x value, all right? So we'll start with a 30-degree angle. The sine of a 30-degree angle is 1/2, always. So if I look here, the sine of a 30 is 1/2, the cosine is the square root of 3/2. So if I were wanting to know what this point is, this xy value, it should be the cosine and sine of a 30-degree angle. That is the x and the y value right there. All right, and so if I look at a 30-degree angle, my x value is the square root of 3/2 and my y value is 1/2. All right? If I were to look at the 60-degree angle, those two should just flip. My cosine or my x value is now 1/2 and my y value is now the square root of 3/2. Because 60 and 30 are complementary angles, and remember their sine and cosine just flip-flop, right? 45 is really easy to remember. 45, both the sine and the cosine, because those side lengths are the same, is the square root of 2/2. You need to be filling in your unit circle. Square root of 2/2 for both your sine and your cosine. We say sine and cosine. I'm going to tell you what people usually confuse. We say sine, cosine, but it's actually x and y up here, right? So the first one you see, the x value is your cosine. The second one you see, your y value is your sine. All right? So when you say, you're going to say sine and cosine, but you have to think yx. Y is sine, x is cosine. All right? Let's fill in the other ones. So if this 30-degree angle has a sine and cosine of square root of 3/2 and 1/2, right? Those are my x and y values. This reference angle should have the same exact sine and cosine. What's the only difference on this side of my coordinate plane? One thing is going to change over here. Yeah, my negative. For which one? My cosine or my sine?
Cosine.
Cosine, because it's my x value. So if you mirror that 30 degrees, you will see that it is also a sine of 1/2 and a cosine of square root of 3/2, but my cosine is now negative. That's what's going to happen all the way up. My 45 is going to be square root of 2/2, square root of 2/2, but my x value is negative. My 60-degree angle over here has a sine of square root of 3/2 and a cosine of 1/2, but my cosine again is negative, right? Because all reference angles have the same ratios. What do you think then happens in third quadrant? They are all what? Negative. So if I look at my 30-degree angle in my third quadrant, sine is negative 1/2, cosine is negative square root of 3/2. If I look at my 45 in my third quadrant, they're both the square root of 2/2, but negative. And if I look at my 60, my sine is square root of 3/2, my cosine is 1/2. Again, both negative. Fourth quadrant, which one is negative, sine or cosine?
Sine.
Sine. 30-degree angle. Sine of negative 1/2, cosine of square root of 3/2. 45, square root of 2/2, square root of 2/2, but my y value, my sine is negative. And then negative square root of 3/2 and 1/2 for my 60. Unit circle is not hard to memorize. You literally have to memorize the first quadrant, period. And then you can fill in the rest of it by mirroring, okay? Let's look at my special angles. If my radius is 1 unit, then over here at 0 degrees, I will have moved in the x value positive 1 and none in the y value, right? Which means the sine is 0 and the cosine is 1 over here at 0 degrees. If I were to go the opposite direction, I will have moved negative 1 unit to the left and none up and down. So again, my sine of 180 is 0 and my cosine is negative 1. Let's look at 90 and 270. For 90, I moved up 1 and didn't move left and right any. So my sine here is +1, cosine is 0. And straight down, my sine is -1 and my cosine is also 0. If I were to ask for a tangent based off the unit circle, I can strictly put sine over cosine, y over x. There will be 2 places where tangent has a problem. Where are those 2 places? Where will tangent have a problem? And you'll say, sorry, there is no tangent. There's 2 places on the unit circle that has an undefined tangent. Where are they? Tangent is y over x. Y over x is tangent. Actually, it's y over x. So at 90 and at 270, I have an undefined tangent, right? 1 over 0 causes a problem. -1 over 0 causes a problem. Your tangent of 0 and 180 is actually 0. 0 over 1, 0 over -1, not a problem. It's just 0. All right? But on your top and bottom, you have an undefined tangent. Pi over 6. So look on your unit circle. What is the sine? I'm going to write it this way. The sine of pi over 6 from your unit circle. What's the sine value of pi over 6?
30 degrees.
So it's going to be 1/2. My sine value, my ratio at sine is 1/2 for a 30 degree or pi over 6. My cosine value is going to be my x. So what is your x at pi over 6? Square root of 3 over 2. How then would I find my tangent? Y over x, 1/2 over square root of 3 over 2. Keep, change, flip, right? 1 over the square root of 3. What do you think I'm going to do there? Over 3, yeah. Just rationalize it. So anything on the unit circle, you don't even have to use a calculator, right? You can strictly go and say, I know exactly what my sine, cosine, and tangent is. And I can find the other 3 just by flipping it, okay? It is built off of reference angles, 30, 45, 60 reference angles. And you can find any of those angles that meet that criteria, all right? If your reference angle is one of those, the sine, cosine, and tangent will be the same. Even if you go past 360, if you hit a reference angle that is 30, 45, or 60, you should know the sine, cosine, and tangent because they will always be the same. The only thing that's going to change is your positive and negative as you move around the circle, all right?